get better and more understand about this problem. Now, the last topic I wanted to emphasize in this chapter is the efficiency. Because the second law is also related to the efficiency, and we told you the efficiency is always going to be less than 100%. 100% is simply meaning is equal to 1. So the definition for the efficiency is, if you burn some gas, you provide some heat, and that is the heat that goes into the system. So that's your input. The output is, once you provide some kind of energy to a system, you're expecting the device will give you the same amount of the energy output. The amount of energy output is what we define as the work. So when you heat up a gas, the gas will expand, it's going to do some work. So that work is the output that we expected. And therefore, be careful here. Efficiency is defined by the output, which is work. And this work is done by the gas. The substance here is simply just the gas. You can think about that as the gas to the environment. Now, Q here is the input. The input is the energy that you provide to this device. And is the heat, H here is the heat to the gas. So you can think of we only look at the heat goes into the gas. It's possible for the gas to release some heat, but that kind of heat doesn't include it in this calculation. Okay, you only use the heat which is positive. Only use the heat that goes into the system, goes into the gas. Now this work is equal to the change of the two different heat. So because the energy is conserved, so the work that you actually do to the system is that you might give the heat to the gas, and what happened to the energy is that some of the energy that you do work, some of the energy will goes back to the environment. So the difference of this two heat is the energy that you can actually do work. If you put these two into this equation, I'm not going to derive this. You can look at these derivation in the textbook. What it turns out is they related to the temperature. So if you have two states, one is at hot. H here represent hot. The C over here represent the cool. So if you have a PV diagram here where this is a P, this is a V, and you have two processes. One process is here. This is process 1. This is process 2. This is the temperature of 2. This is temperature of 1. This is the hot temperature. This is going to be the cold temperature. So if you change the process from a high to low, which could be from here and go to here, then this process is going to give you some kind of efficiency, and you can look at what is the heat change over here and what is the work done during this kind of change of process, and you can do the calculation of the efficiency. And it turns out to be like this. Now, the temperature hot minus temperature cold divided by temperature hot. You can also rewrite this as 1 minus Tc over Th by divide Th at the top and the bottom at the same time. You will get this equation here. Now, this equation gives us an idea how I can increase the efficiency of the device. And that is, you have two ways. One is, the key is looking at this one here. Tc over Th. You want to make this one, we want efficiency to be close to 1. To make this one close to 1, we want to make this one to be very small. How do we make this one to be very small? Well, either you make the Tc very small or you make Th very large. TH very large, meaning you're going to increase the hot temperature. TC very small, you're going to decrease the cool temperature. And that's the way you increase the efficiency. Okay, let me show you one example how we use this to do the calculation. This is one example in the textbook, 27, problem 27. I encourage you go through this problem. You also have one problem online, which is a similar. So this problem gives you a PV diagram. As you can see, this is the PV diagram that you have, and you have three different states: state 1, state 2, state 3. You also have three different paths, A and B and C. The first thing it tells you is one more, so at the end equal to 1. This value, the pressure and the volume are all given, so you can use those values to do the calculation. The first thing you do here is that we are asking, what is the work done on the gas by the environment? Okay, during each one of the steps, which is the process A and B and C. So what is the process A? This is isobaric, right? What is the process B? Well, I don't know what the process B is. We don't have a specific name for that. I know the isobaric is the process C because volume doesn't change. Okay, this one I don't know. Now, to calculate the work done, what you have to do is that you're going to look at the P times change of V. Now, because you are looking at the situation where you are define the work that is the environment on gas. So the work is going to be P times negative P times change of V. So for example, if I wanted to look at the path of A, and the pressure is isobaric, is going to negative 120, and K Pascal, K represent 10 to the third Pascal, which is the Newton divided by meter squared. And what is the change of volume? Well, the change of volume is the final minus initial, which will be the second volume minus the initial volume. That is going to be 4 meter cube minus 1 meter cube. And if you do this, then you will find out this is going to be a negative 3.6 times 10 to the 5th joule. So that's how you find the work. This is the work done on the gas by the environment. You can do the similar thing, and we can calculate what is the work of the B. Now, the work of the B, because I don't have a fixed pressure, but another way that you look at what is the work done by the gas, what is the work done in the PV diagram, is to look at the area under. So the area under this path, which is from the 2 to 3, is this area over here. This area, you can calculate area by trapezoidal, or you can divide this into two shapes. This is probably easier if you don't know the formula of the trapezoidal. If you divide this by 2, then you have a rectangular, you have a triangle, and then you know how to do the calculation. So if I look at the B, and I'm going to look for the area of this rectangular plus the area of this triangle. So what is the rectangular? Well, rectangular, you have negative 60 times 10 to the third Newton per meter square. and the volume is going to be final. The final is going to be volume at 0.3, that is 1 meter cube, minus the initial, which is the 4 meter cube. That is the rectangular. Now for the triangle, it's going to be also the negative 6, and that will be the triangle that you look at. The pressure will be, again, is going to be well, this is going to be the height of difference of the pressure. So you're looking at this will be the base. So here is the base. Now the base is going to be 4 minus 3 minus 1. And you multiply the pressure difference. Now the pressure difference, again, I can use the final, which is 60, minus initial, which is 120, and times 10 to the third Newton per meter square. So if you sum these two, you are going to get the total work. Then this will be a positive number, because this is negative, this is a negative, is going to be positive. So this will be 2.7 times 10 to the 5th joule. Okay, now the path C is going to be 0 because there's no change of a volume, so there's no work. The part B is to determine the net work done on the gas, which you simply sum all these two. And you sum all these two, you will get negative 9 times 10 to the 4th joule. That's you simply sum all these numbers. Now the part C asks you about what is the work done by the gas to the environment. Well, this is going to be negative of the total work that you got from the B. Therefore, it's going to be the negative of this, which will be 9 times 10 to the 4th joule. The D, we ask you to find out what is the temperature. So how do we find the temperature? We need to find the thermal energy. Well, okay, so D, determine the thermal energy. To find the thermal energy, we need to have the temperature. So what is thermal energy? Thermal energy is 3 over 2 K times T. And we need to find the T. Where the T, you can use ideal gas law. The T is equal to PV over NR, where N is equal to 1, R is 8.32, and P times V. So you can find the temperature. I'm going to just write one calculation over here. If you do the T1, which is the first temperature, you use P1 V1, which is the pressure and volume at the state 1, and you divide by 8.32, and the P1 is equal to 120 times 10 to the 3, and the V is 1 meter cube, and divide by 8.32, and you will get 1.4 times 10 to the 4th Kelvin. So this is in Kelvin. You can verify this by yourself. The T2 is going to be 5.8 times 10 to the 4th T3 is going to be 7.2 times 10 to the 3 Kelvin. And that is the temperature for each one of the state. Now, how do we calculate the thermal energy? Well, the thermal energy, you can have 3 over 2 K times T by using the T that you got previously. K is the Boltzmann constant. Another way you can do this is that you can also use 3 over 2 P times V as well. So either way is fine. If we use the temperature, then this will be the first one. If you do the calculation, the first one is going to be 3 over 2 times, okay, this can also be 3 over 2 MRT. So I'm going to use MRT, so because I have a temperature already. So N is 1, R is 8.32. Temperature is, for the first one, is 1.4 times 10 to the 4th. And that will give you the thermal energy, which is 1.8 times 10 to the 5th joule. Similarly, you can find the second one. I'm going to just write down the answer. You can verify by yourself. Okay. The change of the thermal energy. If you're looking at the change of the thermal energy for the process A, then you look for the thermal energy at point 2 minus thermal energy of 1, then you will have the change of the thermal energy. That will be equal to 5.4 times 10 to the 5th joule. Same thing for the B. You can also find this to be U3 minus U2. That will be negative 6.3 times 10 to the 5th joule. C will be U of 1 minus U of 3. That will be 9.0 times 10 to the 5th joule. Sorry, this is a force here. Okay, now point F, we wanted to find out, use the first law of thermodynamics, determine the heat during each one of the steps. What is heat? And what is the first law of thermodynamics? Well, the first thermodynamics law gives us the change of thermal energy is equal to the heat from the environment to gas minus the work of gas to the environment. And so what is the change of thermodynamic? Well, this is the one that we got from the part E. What is the gas to the environment? Well, that is what you got from part A, but it's going to be negative of that. So it's going to be a negative of 1. Okay, because the part A, sorry, this is a part A. The part A is the environment to gas. This is the work done by the environment to gas. It's not a gas to the environment. So when you do this calculation, you have to be careful over here. So if we look at the Q here, for the process A, the Q will be the change of the UA. And over here, you're going to put the positive of the work of gas to environment, which will be change of the UA minus the work of A that we did previously. Okay, so what is the change of the entropy thermal energy for A? That is 5.4 times 10 to the 5th joule. And minus, what is work of A? If you look at part A, this is going to be a negative 3.6 times 10 to the 5th joule. And that means this is going to be sum of these two, and you sum these two, you will get the Q, which is 9 times 10 to the fifth joule. Okay, similarly, I will let you do this by yourself. This B will be negative 9.0 times 10 to the fifth joule. The Q of C is going to be 9.0 times 10 to the fourth joule. So these are the heat. Okay, use the first law of thermodynamics. You can find the heat. Now, the last one that we're going to do is we're going to determine the efficiency of the process. Now, the efficiency of this whole process. 1 to 2, and 2 to 3, and 3 to 1. So, the definition for the efficiency is equal to the work done by the gas and the heat from the environment. And that is and so this is from the part of F. The F is the Q of the process from the environment to the gas. And what about the work over here? Well, the work is done by the gas, so it's going to be a negative of A, because A is the environment to gas. You only use the positive one. So we look at what we got from the F. The QA is a positive word, Q. The QB is negative, so we're not going to use the QB. QC is positive, so you're going to use the QA plus QC. Okay, no QB because it is negative. The work is the total work done by the gas. So if you look at the gas, the total work done by the gas is from the part C. So the total work, you use the work from the C. So here is the work from the C, which is 9.0 times 10 to the fourth joule. So by doing that, and then you will find out this is going to be 9 times 10 to the fourth joule divided by 9.9 times 10 to the fifth joule, and that will give you a 0.091. Or you can say this is 9.1% efficiency. So the efficiency is very small. It should be less than 1. And that is what happened. Okay, so this is the end of my review. Let me just quickly go through the important thing that you have to know. So in chapter 12 and chapter 13, you have to know what is the definition of the first law of thermodynamics, which is this one here. The change of thermal energy is equal to the work and also the heat, where the work is the environment to the system, heat is the environment to the system, and you're going to use plus. If you look at work from the gas to the environment, you're going to put a negative over here. Make sure that you know how to define a process and how do you find the temperature and also the thermal energy for each one of the state. And also know how to find the work and the heat for each one of the process. And understand what is the difference between a reversible and an irreversible process. Mechanical energy, which is this one here, is always organized, is reversible. The random energy, which is the thermal energy, is always going to be irreversible. The second law of thermodynamics have several definitions. We define the efficiency one, which you never be able to get 100% efficiency. We also tell you in natural temperature will from high to low. And the other important definition is to look at the entropy. The change of the entropy will always greater than zero. That is, in natural, things tends to increase the entropy to be more disordered. When you do the calculation of the entropy, you use this equation. Make sure that this one is the energy from environment to the system. This temperature has to be the average and is in Kelvin. Okay, in Kelvin. Efficiency, the important thing, the important things that you have to be careful is the Q. The Q only use the positive and is from the environment to the system. So if you heat up the gas, that is the heat that you're going to use. If the system gives you the heat that is negative, don't use that. I wish you understand what I did for the review, and if you have